There we go. So yeah, I have to do some hand waving at validity first, and I'm fully admitting that it's hand waving because I don't keep up on all the different names that people come up with for validity. I just know the general tendencies. But these are the big picture things, reliability and validity for measurement. I'm going to tell you right now, we're focusing almost entirely this semester on reliability. Validity is a separate animal. Validity is whether or not the name that you've come up with for your factor is the right one. And that's a nuanced argument that you have to build over time with layers and layers of evidence of different forms. So validity for what is always the question. Scales as themselves can never be valid or invalid. That's one of my pet peeves and a number of other people's as well. When you read in a method section that the scale has been validated. No, it's used for a certain purpose and someone has acquired evidence that that is a reasonable thing to do, but it's never like done. You can't have a measure that's just done. So we collect evidence for validity, but that's not a property of the scale in and of itself. Reliability, then, is the focus. Reliability is a precursor to validity. You have to measure something consistently before you can launch arguments as to whether you've measured the right thing. So here are a couple of definitions that I like. It's operationalized in several different ways, and most of that is within the scale itself. So you don't need to collect external information in order to come up with a quantification of a scale's reliability in that current sample. So here are two ways you can think about reliability and validity in terms of errors. Random error compromises reliability. So if I'm taking a test and in the middle of one of my problems, like the fire alarm goes off, and I mess up because of whatever I'm scared, right? That's just random. Whereas if I'm taking a test and I am consistently misinterpreting the instructions, for instance, then that is going to compromise validity. So there are examples of this: acquiescence, or what's the one I'm thinking of? Social desirability, those kinds of things. People responding in ways that are not what you had intended, but they're doing it consistently. You can't tell the difference then. It will look like your scale is reliable, but it may not be valid, and that's where the nuance of the argument comes in. So once upon a time, I had a student draw me this picture, and I liked it so much that I asked if I could steal it, and he said yes. So I thought this is a good way to illustrate it. This would be reliable, but not valid. It's off the mark. This is reliable and valid. And this could potentially be valid, but not reliable, because it doesn't hit the bullseye. So establishing validity is an argument that you have to make using external data. There are ways of doing it internally. We're not going to get a chance to talk about those this semester, I don't think, unless we can keep ahead of the schedule. But do you remember the idea of the construct map? We talked about that last time, that you should be able to order items in terms of their severity or difficulty, and you should be able to order your people as well. To the extent that you get the order right, that's evidence for validity. If my theory predicts why certain items should be more difficult or more severe than others, that's internal evidence that I know what I'm talking about, that I'm actually measuring the right thing. Those types of evidence can be found from what's called explanatory latent trait models. It's the idea that you would build a regression model within your measurement model that predicts why certain items are harder than others or more discriminating than others. And so you get some sort of test as to what properties make items more or less difficult. But most of the time, people are focused on external evidence for validity instead. So this is where we get into lots and lots of labels about different kinds: predictive, concurrent, content, construct, face, blah, 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 blah. People are never going to stop arguing about this, I think. It's just going to be, each decade is going to have a new set of words, and people are going to think that that's the best way to describe it until the next decade, and then it goes on. But these are sort of the big ones. Predictive and concurrent, so it should be related to what it's supposed to be related to. It should predict. So if I have some measure, say, of, let's say, child Pre-reading. I'm trying to think back to the IES proposal I just helped with last week. Alphabetic principle, phonemic awareness, letter identification, those kinds of things, right? I'm a developmental psychologist today. They should predict how well a child learns how to read later on, something like that. These are, if those are valid measures of these constructs. And it should relate to things concurrently as well. Criterion-related validity is harder to come by because it's more definite. A good example of this, though, would be a short form. The goal of making a short form is to get to the same place as the long form, but to do so more efficiently. So then you have a very ready, undeniably relevant goal. Does my short form score correspond well to my long form score? The SAT is supposed to predict college success. The GRE is supposed to predict graduate school success. Ha! I'm living proof that it doesn't. So that makes it difficult to get that kind of evidence because there's rarely that undeniably relevant outcome. Then you end up with construct validity, which is the classic definition, should be related to stuff or not related to stuff in a way that you can predict. This is where it gets tricky, though. Convergent validity, that it's positively it's positively associated with things that it should be. It's not associated with things that it should, but then you have to find these relationships. So they can be not there for lots of reasons that actually make good sense, and it's not your fault. So what would be the purpose of making a brand new instrument? In general, there's some hole that you're trying to fill, right? Either it's a brand new construct for which a measure isn't available yet, or your instruments that exist are not sensitive enough to certain populations. So if it's the latter case, let's say that you have a new measure of, let's go, phonemic awareness, and you correlate your new measure with the existing measures and it's not related. Does that mean that you've messed up? Or does it mean potentially that the old measures, all of the children that you assessed were at the floor, but they had some distribution on your new measure because your new measure was more sensitive to people of lower abilities? That can totally happen. And you can end up with a lack of relationship because of the problems that your scale is trying to solve. So it gets tricky to build these sorts of theoretical arguments as to whether or not your measure is valid when the evidence is going to be conflictory because of the reason for making the scale in the first place. So here are some ways to mess up a construct validity study. Do your homework, pilot testing. We talked last time about bad items, things that you can avoid in terms of keeping consistency in STEM direction, making sure that you allow people to answer the question in as many different ways as possible, including not applicable. You can end up with the wrong theoretical framework or the wrong power. So you don't have enough sample size, for instance. You won't find significant relationships. Discrepant EFA studies, that's another one. And then these are the other things that can come up. Evidence for validity can change over time. So a lot of the items in, say, vocabulary tests have to be maintained as relevant. So what do you think a mouse is? What's your first thing comes to head in your head? What's a mouse? The thing in your hand, right? Do you think that that would be the first definition, say, in 1980? Probably not, right? Things like that can get in the way of something that would otherwise be valid. So these are just some of the ways that things may need to change, and shorter or adaptive is a big one. That's where latent trait measurement models can come in handy. So that's my hand waving at validity. That's it. That's the entire semester. I believe there are entire courses on validity. I would encourage you to take those if you want to know more about it. So now we're getting to reliability and why alpha is bullshit. So before we go there, I want to do just a basic review because you're going to hear the word covariance like a million times out of my face this semester, and I just want to remind you what that is. So variance, remember this idea of a pile? It's how far off the mean each observation is squared. Sum those up and divide by n minus 1. Correlation, you're familiar with. how associated things are on a scale of -1 to 1. Covariance is correlation that's unstandardized. So it's how far off you are on your first measure multiplied by how far off you are on your second, sum those up, and divide by n-2. So covariance is in the original units, and that's what makes it hard to interpret the number, which is why people often refer to correlation. But all of the models that we're going to be working with are going to deal with variances and covariances with correlations as a byproduct of those. So I just wanted to remind you what how those terms are defined. Where those things get tricky. Mean and variance are only separable things in certain distributions, like normal. If you have a binary item, mean and variance are linked together. So for instance, if I have a 0,1 variable that has a mean of 0.5, the variance of a binary variable is its mean times 1 minus its mean. So the variance would be 0.25. And as you can see from the table, it shrinks as you get towards the ends. What that's going to imply is that the idea of error variance in some of our measurement models is going to go away, because how much error you have is dictated by, is yoked to the mean itself. So error variance is only going to show up sometimes because of these properties. The error variance is only available in certain distributions. Another thing that is going to show up repeatedly is this idea of covariance. So if I want to figure out what the expected value is of a sum of items, I just sum those means. But if I want to know what goes into the variance of a sum, the covariances show up too. And this is the definition of alpha. It uses this property. So you end up with the variance of item 1 plus the variance of item 2 is each of those variances separately plus any covariances that they have. And it always ends up with a 2 multiplying that, and the way that I remember that is because if you picture a covariance matrix, it's symmetric. So this spot right here, row 1, column 2, is the same as row 2, column 1. So it shows up twice, and therefore if you wanted to summarize this entire matrix, you would have to have the variance of item 1, the variance of item 2, that should be a 1 right there, by the way, that's a typo, and the 2 of the covariances between them. So the extent to which items are reliable, that they go together, is indicated by this covariance part. That's the part that's important. And so that's why it's the unit of all of the analyses in terms of the measurement models. So in classical test theory, that's where measurement starts off. What do? You sum the items up. So the unit of analysis is the total score. So alpha, Spearman, Brown, all those sorts of reliability formulas are dealing with the total score. So we looked at this slide the other day. You have only one piece of information, the sum across the items. From that, you have to try to figure out how much of that sum is because of true score variance and how much of it is because of error variance. You can't figure that out without making a lot of simplifying assumptions to make the math tractable. So reliability then, the classical definition is what proportion of the total variation is true relative to truth plus error. So this brings up an interesting inconsistency in how reliability is estimated and how it is defined theoretically. If you think about reliability, it's supposed to be consistency. The idea that if I took a test over and over again, I should get about the same score. Or if I step on my bathroom scale, I look down at my weight, I don't like the answer, I step off, I try again. If the scale is reliable, I should get the same number back, right? It's this idea that over and over and over again within a person, that's what defines reliability. But in practice, we don't give the measure over and over and over again. We give it to lots of people instead. And then we look at the properties across people. So this is different in theory than what you would think it would be. So we can talk about the variance of the total as part true, part error. By definition, true and error are supposed to be uncorrelated, so they drop. So then you get back to this original formula. So how do we take two scores and come up with some sort of reliability coefficient, such as, say, test-retest? You've heard of that before, right? You give your test to a sample, you make them do it again at some later time, and how related those two scores are is your indication of reliability. Here's how this works. If we write it from an item perspective, the first item here, y1, let's say it's their score on the first time they take the test, is a function of true score plus some amount of error. Likewise, the second time they take the test, in theory, it should be the same true score. The only thing that's changed is error. So if we put that total variance into the formula here, the correlation of the two, we end up with covariance between the two over the standard deviation of each of these. Y1 is supposed to be part true and part error. Likewise, Y2 is part true and part error. If we FOIL this thing out, which you may remember from 8th grade, but if not, that's okay, I've done it for you. I don't think I could do it in front of you if I had to with any level of accuracy. We end up with true times true plus true times error plus true times error plus error times error. Well, guess what? The errors are supposed to be uncorrelated, so that thing goes away. True score and error is supposed to be uncorrelated, so that thing goes away, and that thing goes away, and we end up with this. So we have to assume the same trait is being measured. We have to assume that the E's have the same variance across time. The outcomes have the same variance across time. The E's are unrelated to each other, and the E's are unrelated to the true score. If you buy all of that, then you can say that the correlation between two single outcomes is the proportion of true variance. So those two scores, how do we get them? Various ways. Test-retest, alternate forms, as well as consistency across items within a test. And I note here the idea that we're using different pieces of information as different people rather than the same person measured repeatedly. Some would say that we violated a principle called ergodicity. That way, that's a popular term in some of the measurement fields. So test-retest reliability. What could go wrong? Well, change. How likely is it that the next time you measure someone, they have the exact same true score? It has to be long enough to where they won't remember the items, but short enough to where they won't have grown or declined. If they remember the items, you're in trouble, because then that violates the validity of the measure of what you're trying to do. And what's the right interval? How long is long enough but not too long? You can end up with different test-retest correlations across different intervals, and therefore that would indicate different amounts of true score reliability, even in the face of it actually being the same. Alternate forms is another one. So for instance, the PPVT measure of vocabulary has two forms in each of it, maybe 3A and 3B or 4A and 4B, and those are supposed to be equivalent. But that is only the case if all of the items are equivalent, not just the sum, and that is really hard to do. What if you don't have test-retest or two forms? How do you get reliability out of one form? Split half. That's one way. So let's say I take all the odd items and I sum those, and I take all the even items and sum those. The correlation between the two halves, that's my reliability. Seems plausible, except then each half is only using half of the information and is likely to be less reliable because of that. So there is a formula that gets used to extrapolate what reliability would be if you had more items, and people use this to try and argue their way out of a bad reliability coefficient. So this is known as the Spearman-Brown prophecy. It actually assumes parallel items. We'll talk about that in a little bit, that the items equally measure the trait, and they do so with equal error variance as well. And what could go wrong if it's not truly parallel? For split half, it's arbitrary how you would divide the two, and that's where we get to our best friend alpha. Alpha is the mean of all possible split half correlations. It is known as a measure of internal consistency. The version of alpha that shows up for binary items, by the way, is called the KR20. It's the initials of the authors of the paper, and it was equation 20 in their paper. That's where that name came from. But here's what I want you to know. When you report an alpha, it's real easy to do, and I have an example of how to do that. It is an estimate of reliability that assumes without testing unidimensionality. Alpha is only valid if the items measure one trait. If not, it's not appropriate and it doesn't mean anything. It also assumes without testing that all of the items are what's known as tau equivalent or true score equivalent, that they're all equally good. The slopes in the measurement model would be the same across items. That's a pretty strict assumption that hardly ever holds in practice, and it assumes the errors are uncorrelated. So there's no additional reasons why the items would be related beyond just the one single thing that it measures. So these are all fairly strict assumptions. They're all testable within a latent trait modeling framework. You have to assume them without testing within classical test theory here. So alpha comes from the difference between the sum of the item variances and the variance of the item sums. So here is the covariance version of it. Alpha is the number of items divided by the number of items minus 1 times the variance of the total, which has all the covariance in it, minus the sum of the variances. So the numerator reduces to just covariance. Here's the correlation version that makes it a little bit easier to understand. Only two things go into alpha: the number of items and the average correlation between them. That's it. So if you want to get a higher alpha, you get more items. So here's a table that shows you what alpha will be if you have a certain number of items and a certain average item inter-item correlation. So let's look over here at the good side here. If your items are correlated on average 0.8, that's pretty good. And you have 10 of them. That's an alpha of 0.98. That's really good. What's a conventional level of good enough alpha in your fields? What have you heard? 0.7? That's pretty generous. 0.8 is the one I'm more familiar with. Here's your 0.7. If you have 4 items and they're correlated on average 0.4. So a correlation of 0.4 squared is 16% shared variance. Doesn't sound like a lot, does it? Not really. That doesn't give me a lot of confidence. If you have enough items, such as 10, you can hit that 0.7 cutoff with an average inter-item correlation of only 0.2. That's 4% shared variance. 10 items is not that many. So here is a plot that I made that shows the influence of the number of items given an inter-item correlation. And you can get above 0.7 if you have 30 items, even if they're only correlated on average 0.1. You can rearrange the formula to solve for the average inter-item correlation given the number of items and given the reported alpha. So for example, the GRE subject test for psychology from 2016, in their test manual, they report an alpha of 0.96. That sounds really good, right? Do you know how many items are in there? 205. That means those items are correlated about 0.1. 1% shared variance. And they charge, what, like $300 for that privilege of 1% shared variance? Are you kidding? So yeah, all you need is more items, and alpha is fine. If you have a bad alpha, that's pretty hard to do, but that means it's not going to go well. So here's an example from your reading that I like a lot because it demonstrates why alpha does not indicate dimensionality in any way, shape, or form. Here is one test that has 10 items, and they are all correlated exactly the same. So this would be very strong evidence for not only unidimensionality, but also tau equivalence. All of the items appear to be equally good. Versus this test over here, it has 6 items, and there are 2 pockets. Items 1, 2, and 3 are more correlated. Items 4, 5, and 6 are more correlated, and then they do share some overlap. Both of these correlation matrices yield an alpha of 0.81. Even though one of them is clearly 2 dimensions and the other is clearly 1. Sir? The one that I added to your reading list last week, it's the McNeish article from Psych Methods. Thanks, coefficient alpha. We'll take it from here. Now, what do you do instead? You report, number 1, you test dimensionality, and number 2, you report something that doesn't make these assumptions if they don't hold, such as our friend omega instead of alpha. Omega is based on the results of your factor model. So we'll get to that instead. So what's missing from alpha and the reason that it can't indicate multidimensionality in the formula? We have the average inter-item correlation, but there's nothing in here that captures the variability in that across those inter-item correlations. It's an average, but we don't know where that average came from. So it cannot indicate dimensionality. It has to assume unidimensionality, and because it abbreviates everything in this manner, it also assumes all items are equally good. So yeah, it's not hard to get a good alpha at all. See now, do you believe me? Yeah. The good news is that if the assumptions actually hold, if you have a scale that is unidimensional and has evidence for tau equivalence, then alpha is a perfectly reasonable thing to do. The question is whether or not those assumptions hold, and whether or not you have a means to find out if they hold. Models give you the chance to find out. Adding things up and hope do not. All right, I think that's a good place to rest. Talk about standard errors and such next. Bag on the GRE some more. So, thoughts, questions? No? All right, well then I will see you on Wednesday. Office hours start now if anybody wants to hang around.